Thanks to organizer for inviting me. It's good to be back to Bonn. I was a trimester postdoc a long time ago in 2018. This is the only week I'm here this semester, but it's good to be back. So today I'm going to talk about isomorphism problems. So really, this is sort of a very small step in a very big sort of surrounding theory. So I want to give you first what is the surrounding theory and how people have tried to attack the problem, namely the isomorphism problem, from sort of different logical perspectives. But then I want to sort of tie this back to the project that I'm currently talking about. So the talk is going to have essentially 3 points. The first part is going to be sort of the overall surrounding theory. The second part is the setup for the particular version of isomorphism problem that I am worried about in this talk today. And then the third part is, of course, results. So let's get started. So isomorphism problem has sort of, again, many incarnations, and not just for different mathematical fields. You know, whichever mathematical field you're in, probably you have a version of your isomorphism problem. But also, you know, even if you're a computability theorist, people don't necessarily agree what they mean when they say the word isomorphism problem. So one version of this is actually discussed already in a couple talks earlier in this workshop, namely the ska sentence, right? Because really, if you think about it, what a ska, okay, so let me rewind a little bit. So the ska sentence uses this L omega 1 omega logic, right? So just a quick reminder, L omega 1 omega logic is the first order logic, but you allow countable conjunction and countable disjunctions. And then, you know, the relevance here is that you have the ska isomorphism theorem, which says that for any countable structure A, there is a L omega 1 omega sentence such that for any countable structure B, that B is isomorphic to A if and only if it satisfies this sentence phi. So in some sense, right, the phi picks out the isomorphism class of A, right, among countable structures at least. And so this can be thought of as sort of a way of formalizing isomorphism problem, but this in some sense is like for one structure, right? So you give me a structure A, I want to understand how difficult it is to understand the isomorphism type of this one structure. And then you use quantifier complexity to count, or the arithmetical hierarchy and beyond, to count the quantifiers in this L omega 1 omega sentence, and then you get Montalban's theorem, right? So this again have been talked about a couple of times, but the ones I want to point out here is that this actually gives a pretty strong connection between definability and computability, namely the two themes of this workshop. So on the definability side, of course, the sentence, the L omega 1 omega sentence, is a definition of the countable, of the isomorphism type of the countable structure. On the other hand, you get, and also this also translates to point number 1 here, which is a definition, sort of a, well, not uniform, but a definition for the automorphism orbits. On the other hand, this translates to, unfortunately, boldface. The computable case is much more complicated, as Barbara Chima told us a couple of days ago. But at least in the boldface scenario, you do get this is equivalent to delta 0 alpha categorical. So that is sort of the pseudo computability content of this. Item 3. Yeah. Sorry. Sorry, what was the question?
What's the definition of uniformly boldface?
No, boldface is probably boldface.
Yeah, okay, sorry. Yeah, I should just say boldface. Yeah. So remove the uniformly, please.
It's a later problem.
Yeah, he just wants to know what boldface means.
Sorry, yeah, okay. My bad. Yeah, but yeah. Yeah, boldface means, so this is in descriptive set theory. So essentially, you're allowed like a fixed oracle for what you're doing. So like it's like computable with an oracle of your choosing. Any oracle of your choosing.
It's continuous for functions, right? If you give an arbitrary oracle, a continuous function does exactly the things that are computable with some oracle. So that's a boldface computable.
Yeah. Okay. I should also say that you don't have to memorize any of these because that will not be on the exam. But also like the actual setting that I work in will be different from these. This is like the take one of isomorphism problem. All right, so there's that. All right, so
It's very bad notation.
my apologies, but I also didn't invent that. Yeah, I didn't invent that. So yeah. Okay, so take two. Take two. Get us a little bit closer to the topic or the title, namely equivalence relation. So previously, right, you look at the isomorphism problem of just one structure. But of course, right, you will say, well, if I have a class of structures and I want to know what is the isomorphism problem there, right, namely you give me two structures that you promise to be in a certain class, and you ask me how difficult it is to figure out whether they're isomorphic or not. And in that situation, of course, isomorphism is an equivalence relation. So very naturally, what you want to do is you want to look at it as an equivalence relation. So I give three definitions here. Really, they're the same definition. The only difference is sort of what setting you're looking at and how much sort of Borelness or computability you want to allow yourself to do. So the first sort of iteration of these definitions is given by Friedman and Stanley. And so C and D are two classes of structures. We say the class C is Borel reducible to the class D if there is a Borel function. So we think of these as, sorry, I should have said classes of countable structures just for my purpose. And really the Borel function is in the topology of you think of, you identify these countable structures as their atomic diagrams, and then you just think of, and you assume you're like, make your language relational, so just for convenience, and then you're just answering yes and no, so you can think of that as a subset of the Cantor set. Cantor space. And then there you have the notion of topology, the usual topology, and then you say if there's a Borel function that takes isomorphic structures to isomorphic structures, then this is called a Borel reduction of the classes. And then you can strengthen Borel, right? Maybe you're a computability theorist, and then you want to work with computable functions. This is standard terminology in computability. You instead call them computable functionals because, as you've seen in Russell's talk, these are where you take the input being a set, so it's not literally computable, but rather you use the input as an oracle, and then you try to output something. So this is a computable functional, but then you do exactly the same thing. If you have two A and B, again, you think of them as their atomic diagram as inputs, and then you want A to be isomorphic to B if and only if phi on oracle A is isomorphic to phi on oracle B, and of course you want them to output structures in D, right? Otherwise, your target space is something else. And then you can even further effectivize this. Namely, previously we were thinking about just structures. We are not putting any constraints on the computability of the structure. So if you further put constraints on the computability of the structures, then you can really think of these structures as presented just by some CE set, let's say Wi and Wj. So now you actually transform your question to equivalence relations on omega, and then you say, you give me an index. I think of them as an index, right, I and j, and they will present some structures in the class C, right? So I have Wi and Wj. Again, I want them to be isomorphic if and only if I take now the honest-to-God computable function f, right? And then I look at what is Wf of I and Wf of j, and I want them to define, again, isomorphic structers in D. So all of these has been studied quite extensively. Yeah. So for my talk, Wi will be n enumeration of all CE sets. Yeah. So there is some sort of subtlety here. You have to worry a little bit about like whether it converges or not, and that's why I like to think of my language as being relational, just to avoid that issue.
So then, if Wi is an RE set, or then how do you what is the difference between isomorphism C and isomorphism E? What is
Yeah. So okay. So
what do you mean by class of structure?
yes, that's a great question. So really so Wi and Wj are just two sets, right? Which I think of as just a point in the Cantor space, right? And then they will define some structure, some L structure in the language L. Now they may not even be structures in C. I don't know. Maybe they're not even structures in C. So when I say they're C isomorphic, what I meant is that when I look at them as L structures or LC structures, they actually are structures in C and they're isomorphic. So there's like a lot of things going into this notation, I guess.
You're encoding the structures of C in some way as RE sets, and then you're also encoding in some different way the structures in D as using the same RE sets.
Correct. Yeah, but the encodings are different. Yeah. So I need to sort of fix the encoding in advance, but again, I don't want to go into the subtlety too much. Yeah. Good. Okay. So really, the takeaway here should be that, you start with this sort of Borel definition, which is good for if you're working in descriptive set theory, but then you sort of iteratively try to effectivize it into sort of a computable setting. That's really sort of the takeaway here. So if you do this, the middle one, the Turing reducibility, actually implies both the upper one, the Borel one, and the lower one, which is the effective one. So that's not too hard to see. But unfortunately, the converse, or I guess fortunately, the converses are not true. So these are actually different notions. But there are actually quite a few results in this direction. And one of the important things is you want to find so-called universal classes, namely the classes that are on top, namely every other class reduced to them. Right? So originally in the Friedman-Stanley paper, they already showed that trees, linear orderings, nilpotent groups, and fields are on top for Borel reducibility, because that's sort of where people look at it the most. And then Kamerlo and Gao showed that Boolean algebra, so they added Boolean algebra to the list. And then Paolini and Shalat and Chris and Ulrich, I believe he may tell us something about that in just a few hours, that torsion-free abelian groups is also on top for Borel reducibility. And then on the effective side, Fokina, Friedman, Valentina, Knight, McCoy, Montalban show that the original structures in Friedman and Stanley are actually also on top in effective reducibility. All right. And then there's another, so this so far is sort of just,
Sorry, so these structures, like for example, on the floor should be computable itself or not really?
You only look at the computable members in these classes. But like, when you define a class, you just take the usual definition.
So for example, Borel, like also you only look at these.
No, when you talk about Borel, you look at all of them. Yeah, it's just that it's just about effective reducibility, right? Because in the effective reducibility, we actually code the structures as RE sets. So if you don't have an RE set coding that particular structure, you essentially don't see it in this definition. Yeah. Okay. All right. But then this point of view actually also provide another way of connecting definability and computability. So there's this definition by Russell Miller, Bjorn Poonen, Schutens, and Sasha over there, yes, that you can actually upgrade the middle one, namely the Turing reducibility, a little bit. So what you want to do is that you not only want the reducibility to reduce isomorphic structures to isomorphic structures, you actually want it to also reduce isomorphisms to isomorphisms. Right? So what that means is that you have this notion called a functor from algebra, but really it's just a pair of computable functionals such that the first one just does what a Turing reducibility is supposed to do. So it reduces isomorphic functions, isomorphic structures to isomorphic structures. And the second part will have to map isomorphisms to isomorphisms. So if there is an isomorphism, then when you take both of the structures, namely their atomic diagrams, and the isomorphism as oracles, then you're going to output an isomorphism of the target structures. And then on the so this is sort of the computability side. On the other side, you have this sort of definability way of looking at this, which is called effective interpretation. This is similar but different from the model theoretic interpretation, because now you allow your domain to just use any finite strings instead of you have to fix an arity for your string. And instead of first order definitions, you allow what's called effectively definable definitions, which is roughly speaking just delta 0, 1 definitions in L omega 1 omega. So again, this is sort of a definability more in the L omega 1 omega realm instead of the model theoretic realm. But then there's this theorem by Harrison-Trainor, Melnikov, again Russell, and Montalban, that these two things are actually equivalent. Namely, if you have two, so here the version I gave is just for two structures, but there is a version of this for classes of structures and even back and forth. But I don't want to get into too much of that. But this is just give you a flavor of things. Is that if you have two countable structures, then one structure is effectively interpretable in the other if you look at the isomorphism class of the structure, right? So you think of that as a category, you throw in all the isomorphisms, right? And then this class now as a category reduces, or there is a computable functor going from one of the isomorphism class to the other isomorphism class. All right, so again, this is another way to look at isomorphism problems and sort of its connection tying together both definability and computability. So I want to take another poke at this isomorphism problem. And this time, actually, this is even sort of earlier, because this is actually the version that Max Stain gave in 1911. So this actually predates all the computability theory, and in some sense, it could be argued, well, controversial, but it could be argued that this is the origin or one of the origin of computability theory. That is, you want to determine, right? So what Max Stain, as far as I understand, he wanted an algorithm, much like Hilbert wanted an algorithm for 10th problem, that he wanted an algorithm that will determine if two groups are isomorphic. And the particular version he gave was for presentations. And that is because really he's thinking of groups as fundamental groups of certain spaces, and then you can calculate the presentation reasonably easily from the, well, depend on how your space is given, but well, let's say you can calculate that. Then, so an example of this will be the following. So you have two groups, and I'll say a little bit about how presentation works as a reminder. So on this side, right, you have this group G. So the presentation has two parts. This part is the generators, and this part is the relators. So on top of the usual group operations that you have, so you can multiply things and you can take inverses and so on, you also subject your group to these relations. So for instance, whenever you see ABA, you are allowed to say that equals to BAB, and then you say A has a 2 torsion and B has a 3 torsion. Okay, so that's what a presentation is. Essentially, you just, from a logical standpoint, you just take the freest group subject to all of these. Namely, if you just look at the free group, and if there's a proof via these relations that one term equals to the other, then you say they're equal, otherwise you don't. That's really what you do. And on the other hand, of course, this group over here, right, is just the trivial group. Right? So you say, I have one generator, but haha, that generator actually is 1. So that's just a trivial group. Okay? And then, for instance, an example of Dane's original question would be, now I give you these two things, right, whether they're isomorphic or not. This, of course, turned out to be unsolvable, and this is the Adi-Robin theorem. Right? So isomorphism problem for finite presentations of groups is undecidable. All right. So this is how sort of I would say algebraists, or at least group theorists, would like to think about isomorphism problem, and do know that this is quite different from how computability theorists, or in particular computable structure theorists, think about isomorphism problem in the previous couple of slides. Because in the previous couple of slides, really you always identify your structure with the atomic diagram of the structure, and then you just think of that as a point in the Cantor space. But then here, right, really what the group theorists want is that, well, really I don't want to think of my group as, just having domain omega. How they want to think of it is they want to think of it really as a quotient of the free group. Right? So you're given a presentation, and then they're interested in knowing if I give you two, really normal subgroups of the free group, do they define isomorphic groups? So this is sort of a very different point of view from what computable structure theories look at. And this is also the point of view I want to take, because both for historical reasons and both for, really this is how they think about it. All right. You can do a little bit better. So I'm going to formalize this, but in particular, I want to formalize this as an equivalence relation, right? So Dane's version is just, I give you two things, can you decide if they're isomorphic or not? Of course, if you have a computable solution to that, then you also have a computable solution to the equivalence relation version. So there's not much point in thinking of that as an equivalence relation if you expect it to be computable. But now we know it's not. So let's try to look at it from an equivalence relation point of view. So I probably should have put this earlier. That will resolve one of the questions. But when I write Fi's, I mean that's just a computable enumeration of all the finite subsets of omega. And then when I write Wi, that's a computable enumeration of all the CE subsets of omega. Okay? So with this, we can define the isomorphism problem of finite presentations of groups, and I really want to think of it as an equivalence relation on omega, right? Because finite presentation being a finite object, I can just code it with omega instead of the Cantor space. So what I do is I just say the following. This is what you would expect. N and I, right? N and I here, N codes how many generators you have, and I codes the relation set. So Ni really codes A1 to An, and then with the relation set, the finite relation set Fi. And then similarly, you do the same thing, but now for finitely generated CE presentations, instead of Fi, you use Wi. So that's pretty, I would say, if you put a gun at my head and have to write down a definition, this is the definition I write. All right.
For the Fi, do we know exactly how many elements?
Yes, yeah. So just, yes.
We know.
Yeah. It's like a completely computable encoding. Yeah. All right. So if you look at it this way, then you can have this what's called computable reducibility. So this has been sort of studied by Ershoff back in 1973, but then there's a long period of time where people really haven't looked at it at all. And then in 2001, Gao and Gerdes sort of revisited this definition and then actually have a nice paper. And then after that, there's a lot more sort of discussion around these. But really, again, this is the same definition as the previous definitions that I put on the, I think, the third slide, where what you want to do is that you have two equivalence relation, E and F on omega, right? So E here and F here. And you want to say that E is below F, right? So for this, I won't have a subscript because this is the only reducibility for the rest of the talk. But what you want to do is you want to say that for every I did say omega. Okay, so for every I and j in omega, right, they're E equivalent if and only if their images are F equivalent. Okay, so that's again what you would expect is that you need a computable function because this is a computable reduction, and then you need that to preserve equivalence. Okay, so under this reducibility, now we have now we can calibrate the complexity of these isomorphism problems, right? Because now the isomorphism problems are on omega, and you have the okay, that's the right side. And then you have the following theorems. So again, it's kind of interesting that group theorists actually thought about this, even predates the definition. So again, this is by Chris Miller. This is back in 1971. So if you remember, Ershoff gave the definition in 1973. So as far as I know, he's unaware of Ershoff's definition. And really, you have to sort of dig through exactly what he proved. But really what he proved is the following.
We're thinking maybe it's Charles Miller?
Oh, sorry, Charles Miller. Yeah, Charles F. Miller III. Yeah, sorry. I learned that from Stefan. Yes, Charles Miller. I just keep in mind C. Miller, but yeah. Thank you. So the isomorphism problem for finally presented group, right? Again, he didn't use the language, but if you take the language that I gave you a couple slides ago, that under computable reduction is actually sigma 0, 1 complete. And this is essentially as hard as it can be when it comes to finite presentations, because it turns out that if you just look at sort of the naive definition, then it is actually sigma 0, 1. So this is in some sense the hardest it could be. And then just actually this year, although we proved the theorem a couple of years ago, with Andrews and Harrison-Trainor, we sort of proved the analog of the theorem, but for finitely generated CE presentations. So this time they are sigma 0, 3, and what we showed is that they are sigma 0, 3 complete. Okay, so these are in some sense sort of as hard as they can be. All right. So this is the group theoretic situation, but I do want to extend this to other algebraic structures as well, because, well, for group theory, if you're looking at groups, these are, well, you can also ask what happens if you just have a not necessarily finitely generated but CE presentation. I would guess that's probably sigma 1, 1 complete, although I don't know for sure. But it's more interesting if you introduce more structures into the theory and then sort of see how they compare. So this is what I want to do, but before I do that, you have to be a little bit careful, because here you're talking about presentations, and not every structure or class of structure naturally admits presentation. So for instance, in a field, right, if you just very naively take a presentation and you accidentally say 0 equals to 1, well, that's not great. So you have to be a little bit careful, and the way to do this is from universal algebra. So I have to introduce a little bit of the universal algebra terminology. If you feel uncomfortable with it, really the takeaway is that I want to look at a class of algebraic structures where presentation makes sense. That's really all the takeaway. But please bear with me for the next couple of slides with some universal algebra. So for universal algebra, the first thing that comes up is this unfortunate naming of the definition. So we say a class of structure, this is one of their fundamental definition, which is a class of structure is a variety. So certainly not the variety in the sense of algebraic geometry, but a variety if the class of structure is closed under homomorphic images, subalgebras, and products. And I'm not going to define what each of those means, but if you try to write down a definition, probably is equivalent to the correct definition. And then you also say that a class of structure is an equational class. This actually looks a little bit more like what you would expect if you really try to copy-paste the definition of variety in algebraic geometry to this situation. But if it is axiomatized by sentences of the form, for every x bar, some term in x bar equals to some other term in x bar. and you're only allowed one universal quantifier and one equation. So no conjunction, disjunction, and no existentials. Okay, and equalities only. So this, in some sense, is I guess generalizing. I actually do not know which definition came first, but this is in some sense generalizing the definition of or the analog of the definition of algebraic geometry, because you're sort of looking at quote-unquote polynomials, so terms, and set them equal to each other, and then see what you can cut out. It turns out that these two definitions are equivalent, and so just to avoid confusion, I'm going to call them equational classes. Okay, but really, again, the important part here is that if you have an equational class, then a presentation actually makes sense. Again, the presentation will have two pieces. You will have the S part, which is the generators. So it tells you what are the variables you're allowed to use to generate your term algebra. And then you have R, which I will call the relations, which is the extra relations on top of the axioms that you use to axiomatize your equational class. On top of those axioms, these are like the extra things that I want my particular algebra to satisfy. So with this, this allows us to talk about the isomorphism problem, right? So I'm going to, for an isomorphism problem, I really think of it as an isomorphism problem of an equational class. So I fix my equational class V, and then the question really is, if I give you two presentations, SR and S prime R prime, I want to determine if they define isomorphic algebras. And of course, I'm going to very quickly think of this as an equivalence relation, but let's at least first, right, look at what are the versions of the question we could look at, because just like in the case of groups, you have at least sort of these three levels you can look at the question. You have computable enumerable, so, well, I'm going to work in the computable setup, so I do want things to be computably enumerable, but that's sort of the most general context in this. Or you could require your S to be finitely generated, but still probably you want your R to be computably enumerable. Or you can just want the whole thing to be finite, right? So the second and the third sort of relates or parallels exactly the two situations we saw in group theory. And then if you just look at these sort of the descriptive complexity on the surface, when you just have two CE presentations, right? The generator. So saying two things are isomorphic is essentially saying that I tell you how I map my generators to the other guy, right? And then I just extend that homomorphically. I need to say it is well defined. I need to say it's injective, and I need to say it's surjective. But when you have infinitely generated algebras, just a priori, just saying there exists a function is already sigma 1, 1. But you can do it in a sigma 1, 1 way. When the generating set is finite, you only need to say there exists like 5 elements that I'm sending my 5 generators to, right? So that becomes a first order quantifier on the first order is essential on the outside. But then you still need to say, for instance, for well-definedness, right, you need to say for every relation in R, right, I actually map it to a consequence of the relations in R prime. So that is an extra universal quantifier, which does go away when you actually go to finite presentations, because now your R is finite, so there's only finitely many things you have to worry about. So again, if you sit down and write down, these are the complexities that you will get. We will focus on the middle part, but I do want to note that this sort of formally justifies that when we set that group is sort of as hard as it can be, right? That means that among finitely generated structures, right, finitely generated group is as hard as it can be because it is sigma 0, 3 complete. And also among finitely presented structures, groups are sigma 0, 1 complete, so they're sort of on top for those. Okay? And then you do the same thing, right? So this is more or less the same slide. I just copy-pasted, but changed things a little bit. I'm now focusing only on the finitely generated presentations, and every set from now on will be CE, so I won't be repeating that. And I will also look at these slightly more restricted finitely generated things, namely I will just allow n many generators. So that will be these Vn's, right? So instead of ni coding that, I will fix a number of generators, so I really just have I coding that. So that's just a slight difference. And the main question is, if I give you an equational class, right, how can I place the complexity of Vn and Vfg against each other and against certain standard benchmarks in this computable reduction? Yes?
We're not assuming anything about the rank or like the necessary number of AIs, right?
No. So for instance, like my first relation can just say A1 equals to A2.
Okay.
Yeah. Yeah.
So can you replace CR by computable?
By you have to be a little bit careful. So you want to play Craig's trick. So in general, yes, like if there's a way to pad, but like your language could be like empty, for instance, then you don't actually have a way to pad, which is, you know, but in most situations, the answer is yes. But that's not how I actually want to think about it, because I don't have a computable enumeration of computable sets, right? So, you know, for my purpose, I can as well just assume they're CE, because that's how I'm coding them. Yeah. All right, any other questions? Okay, good. So, okay, so like I said, right, I want to look at different varieties and I want to compare them against each other and against certain benchmarks. So this is sort of a quick cheat sheet of the things that I'll be looking at. So let's look at up here. These are the 5 classes that I will be talking about today. And I should also say that this is sort of a very early stage of hopefully a multiple paper project. So I'm sort of giving you a preliminary result of what we do know at the moment. But you know, if you have any other suggestions of other structures, I'm very happy to hear what they are. Here I look at UFM, which are just algebras with just unary functions. So I should also say that in the universal algebra setting, usually you do not allow relations. You only allow functions, and depending on your definition, maybe constants, or you think of them as zero-array functions. Okay, so these are in some sense the easiest structure. They're not just like trivial, because if you only have constants, well, there's not much to say. So at least you want some functions, or the unary functions are in some sense the easiest ones. And then, yes?
What do you mean by algebra?
Yeah, algebra, I just mean like a abstract structure, really. So algebra is what universal algebraists call structures, basically.
So in this context, it's just going to be a set of...
Yeah, it's just a set equipped with m many unary functions. Yeah. So you can replace that by structures if you like. Yeah. And then you look at commutative semigroups, commutative monoids, abelian groups. I hope people know what a group is, so I'll start there. Monoid is group minus inverses, and semigroup is monoid minus identity. So those are that. And then I also look at general groups. Okay, so those are the structures that I'll be looking at. Hopefully the names are just abbreviations, so they should be self-explanatory. And then I also need some benchmarks to compare these two. So again, this is due to Koski, Hemkins, and Russell over here. So they looked at certain equivalence relations on omega, right? They defined some of them and then actually compare them, place them under this computable reduction. And these are the ones that I want to look at. The first two are reasonably straightforward. The first one is equality CE. So what that is just say that I and J are equivalent if, as indices, they defined equal CE sets. Okay, that is pi 0, 2, but that is actually not complete. And then you have E0 CE. So E0 is the Vitali equivalence relation or the Taylor equivalence relation, depending on which one you like, from descriptive set theory, but you CE-fy it. What that means is that instead of looking at just 2 points of the Cantor space, you look at Wi and Wj, and this is star equality means that they are equal except finitely many potentially differences. So or in other words, their symmetric difference is finite. Okay, so after a certain point, they are equal. So this is sigma 0,3, and actually it turns out that they're sigma 0,3 complete. And then there's a whole family of equivalence relations I want to look at. Maybe it would have been easier if I first put down E min. So what E min is you just look at Wi and Wj and you think of them as subset of omega, and then you say I and j are equivalent if and only if the minimum element of Wi and Wj are equal. Okay? But I want to extend this a little bit to computable ordinals. So this is actually also already discussed in the definition, so in the paper, so the definition is not new. But you can extend this to computable ordinals alpha, where you really just think, so you have to be a little bit careful. You need to fix a coding or a computable bijection between alpha and omega, right? So once you have that, then you interpret your CE set Wi as a subset of alpha instead of omega. So you just map it through the thing. You do have to be careful because the coding will actually make E min alpha different. So you could have the same alpha and two different codings, and then E min alpha are actually incomparable, for instance. That is a little bit unfortunate, but for the, For the alphas that I will look at, they are really just omega to the n. So just take the standard, yeah, they're coming up back up. Just take the standard encoding via, say, the Cantor normal form. Then you'll be fine. Okay, so this is what these benchmarks are, and so let me just give you the picture. So this is the. Unfortunately, I don't know how to orient it in a nice way so that it's both readable and large. So I chose readable. Sorry, well, readable as in, nicely aligned, not like large enough to be readable. So I hope you can see it. But really, the point is that on the right-hand side, this is the benchmarks, right? So you see we have the E0 CE all the way on top. That's sigma 0,3 complete. We have equality CE, that's pi 0,2 but not complete. And then we have all these like E mins down here. So this is E min of omega, omega times 2, omega times 3, omega squared, omega cubed, and so on. And it's not too hard to believe that if alpha is strictly less than beta, then E min alpha is strictly less than E min beta. Okay, well, again, you have to be a little bit careful with the encoding, but under quote-unquote standard encoding is not a problem. All right, on the left, right, these are the structures that I want to look at. We already see that the groups is all the way up here, so that's G6. It turns out that the particular encoding we did need six generators. Probably you can do it with 2, but we did 6. And then you also have UF21, so that's so the subscript is how many generators you have. So UF is unary function, so we have 2 unary function and just 1 generator. That already is sigma 0,3 complete. So it's already all the way up there. And then you have these bottom ones that are kind of nice. These are abelian groups and unary functions with just 1 function. And it's not too hard to believe, at least for abelian groups, that those really are just E min. So this is really just via the classification theorem of finitely generated abelian groups. So all of them just look like z to some power times z mod a1 times z mod a2 times z mod a3 and so on, where a1 divides a2 divides a3 and so on. And then the how many of those is essentially what is the minimum number of generators you need. So basically every z copy will correspond to like n extra omega. And then the finite parts, you can encode that by just a natural number, and that will give you essentially a full invariant in omega times n, and that will give you the equivalence. What is a little bit more interesting is up here. So the commutative semigroup and the commutative monoids are floating all the way up here as soon as you have 2 generators. And what we do know is that they are above, so for instance, CS2 and CM2, they are above E min omega squared. And I don't know how to fit that on this slide, so I didn't do it. But we also know that E min omega squared plus 1, so just the next one, is not below this CM2. So that is, come on. Okay, that is this fourth point over here, right? Which is that in some sense, if you look at the commutative monoid or semigroup of n generators, then the largest E min that will fit in there is omega to the n. And even omega to the n plus 1 will be beyond that. And really that is because you're just counting how many mind changes you have. You have a question?
What subscript FG mean?
Finitely generated. Okay. So yeah, so that means that I allow you to actually, in your code, tell me how many generators you have instead of fixing it in advance.
You still know how many generators there are.
Yeah. The code needs to tell me that.
Yes.
Yeah. Okay. All right. So how much time do I have?
5 minutes.
Okay. All right. So
More, 10 minutes instead of less.
okay. All right. So this is sort of the specific structures that we're looking at, but I also want to connect this a little bit to general algebraic structures. So it turns out that all these structures, come on. Okay. All these structures, all the way up to this part, not those two, but all the way up to this part, those all satisfy what's called ascending chain condition on the congruences. So I want to say a little bit about that and how that can actually help us to give a slightly more general theorem than the particular examples that we're looking at here. So here's the definition for ascending chain condition. So first I need to tell you what is a congruence without actually telling you what it is. So basically a congruence is just what replaces the role of kernel in universal algebra. Because really if you think about it, you don't necessarily, like how do you define a kernel, right? You say, you really want to say A and B are equal, but then you just say, oh, AB inverse is in the kernel. But in general, you may not have inverse. So you will literally just say A equals to B. So that becomes a subset of A squared instead of A, but it works exactly the same as you will expect a kernel does. So what you want to say for ascending chain condition on congruences is the following, is just that for any sequence of congruences that keeps going up, eventually stabilizes. So this is the usual ascending chain condition. Or conversely, you can do it on quotients, right? Because again, congruences essentially serve as kernels, so every congruence will define a quotient. And then you say that any sequence of quotients, again, have to eventually stabilize. But that kind of becomes descending, but whatever. This is called ACC. I did not invent that, so I will use the customary definition. And then we say a class of algebra has ACC if every algebra in it has ACC. It turns out that you only need to check the free algebra because the definition, it is preserved under quotients. And so as long as the free algebras are ACC, the whole thing is ACC. So this is something that as an algebraist you may have heard Noetherian. This is exactly the same thing in the case of rings, but we're really just generalizing that here. But also it is, well, depending on which one you're looking at, but all these classes that we looked at, the unary function with only one unary function, commutative semigroup, commutative monoid, and abelian groups, they all have ACC. So really sort of this theorem, the following theorem, this one, sorry? Yeah, finitely generated, yes, sorry, yeah. If you're not finitely generated, then yes, you can, yeah, finitely generated. Right, so in some sense, right, this theorem explains some of the behavior before, but of course the exact calibration when comparing that with E min is not explained by this, because that could, depending on which variety you're looking at or equational class you're looking at, they could be different places. But here's the sort of the general theorem, is that if you have an equational class such that, again, the finitely generated ones, thank you for correcting me, has ACC, and we need this pesky little condition that the isomorphism problem for finite presentation is decidable. We've gone back and forth trying to remove that, and then we failed a couple times. So anyway, this is the safe version. Then you have the following two things. So one is that, so these should actually be strict less than, not less than or equal to. So they're strictly increasing, the VIs are strictly increasing all the way up to VFG, and VFG is below equality CE. That should also be strict. The reason for that is because VFG is actually delta 0, 2, where equality CE is pi 0, 2. So this is sort of what explains why in the previous picture all the things are below equality CE, and then you have sort of two more things all the way on top. Yes.
You said that equal CE is not, or is pi 0, 2 but not complete.
Yeah, it's properly pi 0, 2.
It's properly pi 0, 2, so it's properly, like, it's not anything lower, but it's also not complete?
It's pi 0, 2, not complete, but not sigma 0, 2. So in particular, not delta 0, 2.
Okay.
Yeah.
Interesting.
Yeah. Right, okay. Yeah, so naturally you have the following question is that do you actually get an isomorphism problem in the degree of equality CE? That we don't know. But let me just revisit the picture, but this time with this, very nice LaTeX encoding of my handwriting, where you see, really what I want to show is that this gap is extremely large, even though it looks very small in the picture. That is actually a sigma 0,3 complete and a pi 0,3 gap. So that gap is very large. And this gap is also large because from here and below, these are all delta 0,2. And that is properly pi 0,2. So this gap is also large, right? So we do not know anything in these gaps. So I think that will be a very interesting question to ask, is that, does any isomorphism fit in those gaps? And if not, why? Or if yes, give me an example. This is just revisiting the sigma 0,3 completeness. Like I said, G6 and UF21 are all the way up there. What is also interesting is that you remember we have this like pesky little condition where you want the isomorphism problem for finite presentations to be decidable. We actually do not know. So we do know that for groups that's not decidable, that's the Adi and Robin theorem. But we do not know if the isomorphism problem for even UF21, so again, just structures with two unary functions and one generator, we do not know if those finite presentations have decidable decidable isomorphism problem. So if anyone knows, we will be very interested to learn that. So I will end with a few questions. First is that we showed that ACC, well, not quite implies below equality CE. You need this finite presentation isomorphism thing. But the question is, are these two things equivalent? I think it will be particularly interesting if they're equivalent because, again, this will connect not definability, but algebraic properties of the algebra to the computability of the isomorphism problem. So I think that will be particularly compelling, although we were not able to prove that. And then I'm also interested in knowing if there are things in those gaps, right? So, and of course, I would like to know if they're natural examples. It's not terribly surprising that if you can cook up weird examples, of course, we're not able to do, but we're particularly interested in looking at sort of natural examples. I'm asking all the algebraists here, if you have any natural example that you feel will fit in there, I will be willing to learn what you think. And then there's this other question, which again, I want to tie back to the original sort of other types of interpretation of isomorphism problem. So in those other situations, you actually have a very nice sort of correspondence between definability and computability. And my question to the audience is that, is there such a correspondence here? Namely, for computable reduction among isomorphism problems, perhaps you want to add in functoriality, just like what people have done. Does that sort of admit a definability characterization, I don't know, maybe via some sort of L omega 1 omega interpretation or something else? Again, I think that's a very interesting question. So I will stop here.
Have you considered, so I don't know much about universal algebra, but have you considered looking at the question of structures having presentation from like a category theoretic point of view? Like in monadic categories, every object is a quotient of a free object?
No, I have not thought about that. Yeah, yeah. That would be interesting, so we can chat about that, but yeah. The project was strictly only about the universal algebra set.
Other questions or comments? Okay, let's thank Turbo again.